My chair. It's working?
It's working.
Okay. Hi everyone. Like today, I want to introduce about a little bit about zkP and also about the project that I'm working right now, the zk memory. I'm works as the founder of Orochi Network, and I'm a volunteer at zkP Lab. Okay, so here is the agenda of today. So I'm going to introduce about myself and the intro to zero knowledge proof. And we have overview about the project, and then we go to the specification and the growth potential of the project. And after that, it will be the Q&A. Okay, just like I introduced by myself, I'm the founder of Orochi Network. We do the zkP stuff, MPC for threshold signature, zkVM, and like we want to provide the verifiable randomness and verifiable computation for all people. It just happened again.
What?
Okay. So here is the current situation of zero knowledge proof around the world. Like everything is heavily in development. Like you can see a new library going to implement this, just like the thing that happened to Nova and Halo 2 with the KGC from the PhD team. Besides that, there are new paper public like every month. So it really hard to catch up with the academic side. Like we need a community to work together, like share the document and so do the work, the seminar, so people can share the knowledge with each other, so we can catch up with the academic side. Besides that, for the engineer people who do software engineering, it's really hard to tell how my code working or how it's not working, because to understand like everything and even understand the circuit that you write and how the proving system works, you need to dive into the detail and like the mathematics stuff, and it really tough, and it prevents people to understand more about zero knowledge proof. And then we can see that every circuit is very complex. Even for the someone to already have experience with zkP, so they can make some mistake and missing some constraint, and they may not detect the issue. And the most dangerous is maybe some over constraint, like we have more constraint than we need. So something like maybe it's have error and it will pass some case that we're not aware of. And the security for zero knowledge proof is one thing that we still have to figure out how to deal with it. And we need like a tool to detect for the error of the circuit. And every kind of these tools still under development. And then as you see here, like we have academic, engineering, and social security. And let's figure out which is the best like area for zero knowledge proof to develop. Like as you see here, if we combine the academic and engineering, we can have something that it may work, but it's not secure. So if you try to combine the engineering and security, like you can make it work and make it secure, but you don't know why and don't know how it works. And then we combine the academic and security, like it actually understand about the zero knowledge proof, but people cannot actually implement implement something that someone can use. So we need three areas to combine together to create a space for zero knowledge proof to develop. And I see that it really it's like the biggest challenge for zero knowledge proof, because my friend, like, he worked on the cybersecurity, and like he get a bunch of money from doing audits and doing the red team attacking and stuff. So there is no incentive for him to jump into the zero knowledge proof. And but we need the people who have different mindset in security and academic and engineering to go together to solve this problem. Okay, in this talk, I will talk about very like simple like experiment, like the Schrodinger cast. Like, anyone hear about the Schrodinger cast? Oh, well, please. Yes, let's plan it first.
The Schrodinger cat is like a mental experiment about quantum mechanics. That is about, like, if you put a cat in a box and then you make a mechanism that kills the cat depending on the radiation of a radioactive material that have a half-life of X, and then you wait that X, like, according to quantum mechanics, until you open the box. The system doesn't collapse quantically, and at the same time, the box, the cat is dead and not dead at the same time.
Yeah, perfect. Everything perfect. Yeah. So there is also a cast, but there is no radioactive in this box. I have one box and just normal cast. So the problem is right now I have to prove with people that what is inside the box. So anyone figure out how we can prove to the other people, like, we have the cat inside the box? The question, the answer is very easy. So don't put too much effort into that.
Opening the box. Opening the box.
No, you don't. You don't. Okay, it's one way. This is one way to solve the problem. That we don't do that here. Like we try to prove the cat inside the box with the zk stuff. Yeah. So we don't open the box.
It's zero about the
Yeah.
part of the cat.
Okay. Yes. Okay. Also one good way to prove. Yeah. Like, or you can shake the box, and then the cats will get hurt, and then it will create some sound. Or you can call it name. Just like we don't actually open the box, but we can know exactly what's inside the box. But in zero knowledge proof, we have the cards in the information, like the sensitive information, like the transaction, like the computation, like the cross-chains transaction, and we're going to put it inside the box. And the box is built by mathematics and homomorphic encryption. Like, it is the box that we have, and we do the same thing. We do the same methods to prove that there actually a box inside there's actually a cat inside the box. Okay. And then today I'm going to the main part of my talk. It's about the zk memory. Like, right now there are many projects. They do the VM, they build the zkVM. So the idea of zkVM is, like, just like Leo mentioned yesterday, like, there are two ways to do things. The first way, people try to build zk app and zk application, and it is application specific. And Leo try to build a tool, allow people to build the zk application. And another way is build a runtime that have everything can prove in zk. And that's why there are many projects, many labs put a bunch of money to do research about zkVM, because they believe that just need a zkVM and people don't have to write a circuit anymore. I also believe that. Okay, So right now, everybody have to handle the memory, the very important parts of the VM themselves. There are no standard for it. And I just try to figure out how we can build the layer 2 thing, just like we build a modular, like you just install the bucket, and then you can choose several components. You want the memory, you install the memory. You want the CPU, you install the CPU. And then you can have the storage and the more stuff, and you wiring those stuff together. So you can actually build the machine that what you want to see in layer 2. Okay, so let's make the problem much more open. Like we can see, we have one question like what is the memory? So the storage is some sort of memory, but it persists. Like the data is not losing when you turn off the computer or something. So, and then the stack is the memory with a pointer. So when you write the data, you're going to, like you write data, the pointer going to shift to the right, and then just so on. So actually it did the same. It also the memory. And the register of the CPU can be simulated by several memory cells. And just like the zkVM is just about the memory. And the rest of those stuff, it is about the operation code. And the opcode will change the state of the memory, the stack, the storage. Okay. And then a question that I received from CJ about why we need to commit the memory. Like every computation, when you do and you write the circuits and you build this constraint between these two values, actually, like if you change the value or not, maybe if you do the wiring, like the constraint into values, if you change something, like in the middle of proving step, like it's going to get the wrong result, and your result cannot be valid by the verifier. So the same thing we try to do with the memory, like we try to constrain every chain of the memory. So when people try, like the prover going to cheat, they want to change the data, and everything like the proof going to be invalid. So it very like meaningful to the private computation, like when the prover do not reveal any information to their client. Okay. So let's think about the memory. Like the memory is very simple state machine. It just has like two opcode, read and write. And you just make sure that you read the data on the same location. Will be the value will be the same as the previous write into that address. And it's really simple. And to prove the execution or of any kind of machine, we need the execution tray. We build up the tray, we fill with the table, and then we ordering everything like by address, and then also with the time log, as you see here. And then we can have the location and then the read write on that location. And we just need to make sure that previous write will provide the value for the next read from in the same memory address. So with the memory tray, it's very simple and it's very easy to prove. But we may have to deal with several problems, like the memory. When we build the memory for zkVM, it can be like bigger than maybe several terabytes. It can up to that size. And there is one kind of problem that we have to deal with. Like for example, we build the zkVM, and then we call it one memory cell, and it may be like 64-bit. And we want, in the perfect world, that we want to prove every cell of the memory. But what happens if some people try to write in the middle of 2 cells? We also have to handle that. And we translate to some sort of 3 write opcode. Like when you write into the middle of this, we try to translate into write opcodes. And it will be like writing 2 cells at the same time. I mean, one by one, yeah. And there is much more issue from the memory, like reading format and pretty much stuff that we need to handle. And there is one way that people try to use to commit the memory states. Right now, they use the Merkle tree proof. Like I think like right now, zkVM project also use the Merkle tree proof. And the Merkle tree, the problem with it is the proof to open any lib, like any lib over there, you need to cost a lot, and the proof size really big. Like depend on the height of the tree, like the height of the tree, you need to open and create a path to the roots. Like it's either the Merkle tree root, Merkle tree proof, and it really costly. Like the more point you want to open, the more data we have, the proof will be bigger by design. Okay, and then like my friend at the ZK residency, he have one idea, like use the KGG commitment to commit the memory. So the idea of KGG commitment is it have advantage in the proof side. Like we just have like the constant size of like one point to open to any point, any witness, maybe at the same time, and then we can verify the witness with the same cost. Anyone have a question regarding to the KGG commitment stuff? Like, actually, like we have the P here, like when we open a witness, and when we open a witness, we need to calculate as the E point, we need to evaluate as E point, and then we have this value, and it will be P pi here. And also we need to provide pi in next step. Oh. So when actually we put the value over there, like Y, and then S and I over there to there, it will be the same, like after we do the transformation. So it will equal to maybe like could I have one pen? It may be equal to something like this. C F and then we have like this. Like we can have something like this when we try to transform both sides of the equation. Okay. So like we can use the Verkle tree, like Verkle tree using for vector commitment. And a long time before, like people do not actually use the KGG commitment in the Verkle tree. And like we can, in our approach, we want to combine the KGG commitment with the Verkle tree, so we can have the constant proof and also the verification time. as you see here, like different from the Verkle tree, every Verkle tree will have like k leaf on the lower level, and then they have one parent node, and at the same level they will have like k node with the same level, and then they combine to the upper node. And every time there are every red around here, like with using the KGG commitment into a polynomial. So here we have one polynomial, and then also every node here, if they have like children, like they will need a polynomial to commit to that polynomial. Yes.
So the proof, when we use the KCG in the Verkle tree, the proof is not like the Verkle tree proof. You don't need to kind of give like all the branches, or why is the
yes, like the proof, like every like children here,
yeah,
they will commit to one polynomial in the parent, in their parent, and then the parent going to commit to their grandparent, also polynomial.
Yes.
Yeah. I think right now, like there are for our approach, for the current approach, it will cost you like you need to provide the path there to there,
Yes.
but it just cost like maybe log k of n to get back to the root.
Yeah.
And for Verkle tree, the good point is you can do the trade-off between computation and the proof side. Like for better computation, like you can have smaller k. Like if there is smaller k, it will be faster. But if there is more k, so we have like the computation will harder to solve, but then the proof size will be small. So you can choose the trade-off, like choose the k and choose the L, then like the k of the tree to make sure that your proof.
If k is bigger, the height is lower.
Yes.
Shorter. Okay, I understood that.
Yeah. And I think that they also, like in the document I sent to the group, they a link that they try to improve this. Like even you can open any point in this tree with a better and shorter proof. Yeah, I will give you the link.
Why is it better to use the KCG polynomial commitment than a normal fraction?
For the polynomial.
Yeah.
Okay. For the Verkle tree proof, you need to prove that every your sister node.
Yes.
Like you go there up to there,
and
then you have to prove your sister node as well, and then you go to the root until you go up to the root. So like you have to create a path up to the root.
Yes.
So for Verkle tree, you just need to care the commitment here.
Yes.
And you don't need to actually like prove your sister proof, prove the sister node.
But you don't need to prove your sister because of KCG or because of the
because of KCG.
Okay. So
because like we commit, so we can open as any leaf here. Yeah.
Okay.
Yes.
Awesome.
Could you repeat the question? Like
yes.
I think like this Verkle tree used for the commit the data, and we will not actually like prove the data here. Like we're going to commit the value here, into the polynomial in the parent node. Yeah.
So the top polynomial, is that a combination
The top of the tree is also a polynomial. Yeah, but the improvement, they try to use this and combine with random linear combination or something, and then they can actually improve this with like shorter proof. But that guy, he just write a blog and like nothing have been formal verified. Yeah. I think like every leaf there we're going to, yeah, we represent for the state of the machine.
Each branch, I mean, each branch represents a certain step. I have vision and trace.
Okay. Let's like right now, the first thing we try to do is we create a table, and then we have the time lock here, and then we have the instruction, and then we have address, and then we have value, and with the data. With the data, we're going to construct like the Verkle tree from the data. So we actually like every row in the table will become it to the tree.
So
yes.
Every operation is
Yes.
Every step is
yeah. So like for this like you cannot cheat at any point here. Yeah. Yeah, it is like we try to prove this state. Right. Yeah. If we try to like just do the KGG, maybe we have problem with like it depends the size of this table, like the tray table is very big, and we may have some overheads with KGG. That's why we add the Verkle tree combined with Verkle tree with KGG to solve it. Okay. Yes.
So you say like the premise like what's the memory
like memory tray and memory state going to be the every leaf of the tree, and then the children going to commit to the polynomial here. It is here. Like on the top level, like there is another node, and it's going to combine. We'll have the K child, and then it also commit to another level, the prime office, and just yeah. Yes, every memory state early, and then at last we have just one point on the top.
So what is at the bottom?
Yeah. Like bottom, like what depend on how many, like how high your tree is. It's called L, and the number of nodes in one parent. Like each parent will have K nodes. So let's see if I have K equal to 3. So we have this 3, And then we have 3. And then we have this. And we have this. And maybe like I create another mod to have the perfect tree. Yeah, like it is a perfect tree with k equal to 3. Yeah, but in practice, maybe people choose like 16 and also 32. And some people only even show key equal to it is really big number. But when we choose a big number, we have to compute everything harder. Like you cost in the computation, but it costs less on transfer the proof. Yeah.
Why do we need a group by the K?
Yeah. Like group these stopped with K.
Already know one factor.
I think like yeah, good question. I'm also wonder about that. Yeah. I think like it is about the proving like the constructor. Like people try to solve this with like form with the vector commitment. It costs about, and with this I think like people try to solve with KN. Like that's why K, everything depends on K. So if you adjust this K, you can actually trade off between like the proof size and computation.
We have a small setup.
Yes.
We can use a small setup for every small program. We don't need to a long program, right?
No, it's just 1 point here. Like if you commit, it's just 1 point. In the end, it's just 1 point. Yeah.
Just keep the group.
Yeah. And then if there are any point, specific point here, you just need to provide the path. But provide the path here is very simple. Like you have and this path I'm going to provide here is my path is 2, and then my path is 2. So the path to my node is 2. Like for Verkle tree, it's very easy. It is 2 and it is 2 here. It's very easy to identify one path. Yes.
So are you saying there's like one component very small?
Yes.
So all the like only just like very small.
Actually, it's going to have the commitment here. And then yeah. And then the box, the level, they have the commitment here. Yeah. So you don't have to hold everything as long as yeah. Yes. I think like you already have the path here. For example, here 2 and 2. You go in open to open right here. It's 2, and you also open 2 here. Yes. No. Like you open here and open here. Yes.
So isn't there like the idea like the group of the public signal and then external validate, like you run the program and check that the root matches the memory.
Yeah, I think like the thing we try to do here like is open in the path to the root.
Opening the flash.
That like open in the path that from the leaf to the root.
Yes.
Yes.
But from the point of view of kind of proving that the memory operations are correct,
Yes.
isn't it like you just make like the root a public signal and then the verifier checks that his execution matches the root?
Like it is like the proof of membership that prove that one leaf belong to the this root. Yeah.
You can prove that one leaf belongs, but how do you prove that all the operations are correct?
Yeah. So like it need to belong to this, and also like the instruction need to follow the order of time slot here.
Yes, yes.
So like we need to put maybe the tuple of this into the every state.
So if you have another set of constraints outside the tree.
Yeah, yeah.
Ah, okay.
Yeah. Okay. So here is the milestone that we put for this project. The first, we need to implement the zk memory at the state machine, and also we can extracting the memory state. And the next step maybe support Hello 2 because we want to see it to be implemented in the zkEVM project. And the next thing is to support Nova and Supernova. Right now, like my team member working on coding scheme for vector commitment, and then maybe after they submit the paper, I will also publish it. So here, let's discuss about the potential of this project. Actually, like we can build a distributed file system and also build a zk file system on top of it. It's not just about the memory anymore. And in the underlying, we can build the database. Like I talked to my friend about the idea that we build like two things. The first thing, we can use the Verkle tree for the data commitment. The next thing is like we build like a B tree to index the data. So oh. Okay, this idea a little bit crazy. Like I have the Verkle tree here. And I have a 1B tree here. Yeah. It's not the same. Like in this B tree, I'm going to index the value, and I want to build a map from like this value. I'm going to map it into this. So I need a proof of this. Like if we can do this, we can actually prove the lookup process. Like you run a query and then you return the data, and then you can. The first thing with Verkle tree, you can prove that this data it belongs to this tree, and then with the B tree and this proof, you can prove that the lookup process is correct. And right now we also try to do this, but we hope that we can also build something called the zk database. Like actually, like people can read and write approvable data. It's not just about a centralized server that people put data on that. And also we want to support on zkVM project. Yeah, thank you. Thank you, everyone. Please. Yeah. Right now we try to make the interface very easy for people to use. Like just like I mentioned about the machine with 2 opcodes, like people just need to do is maybe involves the opcodes, like you tell the zkE memory to read or write on specific address, and after that it will generate the witness that is like compatible with your proving system. Yeah, that is what I'm thinking. And the cool thing with when we combine like the memory, zk memory with the Nova, if we can actually increase the data, like grow the state of the memory. For example, Nova provides something like IVC, like it is like incrementally verifiable computation. Like you can have this execute by sequence, and if you store every context at this point, you can resume this computation. So I think like for zk memory, we can use like and we use to record every state of. Are there any questions? For the storage, DB storage. Yes. I think right now there is one project on Mina protocol. They call and they are compatible with our project. Yeah, the project that we build is like I don't know, CFSIO. Yes, CFS. Well, like we try to build the database, but with the proof of like it's pretty much stuff that we try to do with the project. Yes. So is I think like they know technical issue with it. Like with the current development of Nova, we can do it just about like all the time, and we can put on the project. Okay. There are one more thing about like people actually can stand the tree. Like you have a don't have to think about the area of the tree or yeah, yeah. Like when we do about the thing, so have some scale. Yeah. So
So that point is because you want to use KH. Why we achieve that extent? I think this part I do not have because like people on having the team that use it, like which completely. I think completely try to do so. Yeah. It's probably a